Dear students, in the previous lecture we have discussed about the basics of differential equations and what do you mean by modeling a physical system, and we have also discussed about the different types of solutions of differential equations. They are general solution and particular solution, and we have also discussed about initial value problem. And these are the things that we have discussed in the last lecture. Today we are discussing sections 1.2 and 1.3 of Kreyszig, Advanced Engineering Mathematics. Okay, let us start. Here we will first discuss the geometrical meaning of y dash equal to f of xy. And here we are considering a basic differential equation, ordinary differential equation, y dash is equal to f of xy. From calculus, we know that derivative of a function always gives the slope of that particular function. Hence, a solution curve of equation number 1 that passes through a point x0, y0 must have at that particular point, the slope y dash x0 equal to the value of f at that point. That is, y dash of x0 equal to f of x0 and y0. Using this fact, we can develop a graphic or numeric methods for obtaining approximate solutions of ordinary differential equations. In this case, we are considering y dash is equal to f of xy. And this helps to a better conceptual understanding of an ordinary differential equation. Moreover, such methods are of practical importance since many ordinary differential equations have complicated solution formulas or no solution formulas at all, whereby numeric methods are needed. First, we are discussing graphic method of direction fields. Here we are considering the graphical representation of the solution of y dash is equal to f of xy. Okay, we can show directions of solution curves of a given ordinary differential equation by drawing short straight line segments in the xy plane. You can see the figure. This gives a direction field, or it is also called a slope field, into which you can then fit solution curves, approximate solution curves. This may reveal typical properties of the whole family of solutions. Here in the figure, it shows a direction field for the ordinary differential equation y dash is equal to y plus x, and it is obtained by some computer algebraic systems, and some approximate solution curves are also fitted in. And in the figure you can see direction field of y dash is equal to y plus x with three approximate solution curves passing through 0, 1, 0, 0 and 0, minus 1. So we have three solution curves respectively. Next, we are considering a numerical method. Given an ordinary differential equation y dash is equal to f of xy, and initial condition is also given. So here we are considering an initial value problem, and the initial condition is equal to y of x0 is equal to x0. Euler's method yields approximate solution values at equidistant x values. x0, x1 is equal to x0 plus h, x2 equal to x0 plus 2h respectively. And those values gives y1 is equal to y0 plus h of f of x0 y0, y2 is equal to y1 plus h f of x1 y1, etc. See figure 8. In general, we can say yn equal to yn minus 1 plus hf xn minus 1 yn minus 1. So this equation, that means yn is equal to yn minus 1 plus hf xn minus 1 yn minus 1. This is a general solution where the step h equals some very small values like 0.1, 0.2, etc. We will consider a table for that, or a small value of greater accuracy. And here you can see in the graph, first Euler step showing a solution curve its tangent at x0, y0, step h and increment hf x0, y0 in the formula of y1. You can see the graph. Please see the graph and check. Now the table shows the computation of n equal to 5 steps with h is equal to 0.2 for the ordinary differential equation number 2 and initial condition y0 is equal to x0 corresponding to the middle curve in the direction field. We shall solve the ODE exactly in later. For the time being, verify that the initial value problem has the solution y is equal to e raised to x minus 1. So here we are considering a differential equation y dash is equal to, you can see equation number 2, and the solution is given to you. Okay, we will solve this in section 1.5. This solution curve and values in the table 1.1 and are shown in figure 9. The values of that particular function and the table and the graph is shown in figure 9. These values are rather inaccurate. Therefore, the errors y of xn minus yn are shown in table 1.1 as well as in figure 9. Decreasing h would improve the values but would soon require an impractical amount of computation. Much better methods of a similar nature will be discussed later. Okay, so this is the numerical method. Euler method is basically a numerical method for solving differential equations, and here we have discussed two types of solution. First method is called graphical method and second method is called a numerical method, that is also called a Euler method. That is we have discussed till now. Now we are considering another method of solution, commonly used method for solving differential equation, and that method of solution is called variable separable form. Okay, so here we are discussing that. So separable ordinary differential equations and its modeling. Many practically useful ODEs can be reduced to the form g of y dash is equal to f of x. Here you have to observe that in the LHS you can see a function of y only, and in the RHS you can see a function of x only. So you can do this by purely algebraic manipulations. Then we can integrate on both sides with respect to x, obtaining integral g of y dash dx equal to integral f of x dx plus c. On the left we can switch to y as the variable of integration by calculus y dash dx is equal to dy, so that g of y dy equal to integral f of x dx plus c. If f and g are continuous functions, the integrals in equation 3 exist, and by evaluating them we obtain a general solution of equation number 1. This method of solving ODE is called method of separating variables, and equation 1 is called a separable equation because in 3 the variables are now separated. X appears only on the right side and y appears only on the left side. So this is very important. So if you can manipulate the given differential equation in this form, then you can solve the equation by direct integration. So this is one of the most powerful technique to solve differential equation. So we are considering an example for that. Here a differential equation is given, y dash is equal to 1 plus y square. So you can immediately do the algebraic manipulations. Y dash means dy by dx, which is equal to 1 plus y square. You can take 1 plus y square in the left hand side, then you can write dy by 1 plus y square equal to dx. By direct integration you will get y is equal to tan x plus c. It is very important to introduce the constant of integration immediately when the integration is performed. If we wrote tan inverse y is equal to x, then y is equal to tan x, and then introduced c, we would have obtained y is equal to tan x plus c, which is not the solution when c equal to c not equal to 0. So you have to be very careful to add the constant of integration immediately when the integration is performed. Otherwise, you will get wrong answers. You have to be careful. And another example also you can see y dash is equal to x plus 1 e raised to x y square is also separable. Then also you will be getting a very nice solution like this by immediate integration. Now we are considering an initial value problem, IVP, initial value problem, bell-shaped curve. So what we are doing is we are solving a differential equation y dash is equal to minus 2xy and the initial condition y of 0 is equal to 1.8 is given. So immediately you can separate in the variable separable form dy by y is equal to minus 2x dx. Then you integrate, you will be getting natural logarithm of y is equal to minus x square plus c. Or you can write y is equal to c e raised to minus x square. This is the general solution from it. And the initial condition y of 0 is equal to c e raised to 0. You will get the constant of integration as c equal to 1.8. Hence the IVP means initial value problem has the solution y is equal to 1.8 e raised to minus x square. This is called the particular solution. So first we have obtained the general solution y is equal to c e raised to minus x square. Then by imposing the initial condition we have obtained the particular solution y equal to 1.8 e raised to minus x square. So the graph is also given and you can see that it is something like a bell, so it is called a bell-shaped curve. So this kind of bell-shaped curve is having very much importance in physics. Now modeling. So actually whenever we discuss differential equation we will discuss modeling, because modeling means we are understanding a physical system by using differential equations. So here also we are discussing modeling. And the importance of modeling was discussed in the previous lecture. Here also we will discuss modeling. Separable equation yields various useful models. So here we will be discussing many models, basically two models to discuss about the power of differential equations. Okay. First we are considering the radiocarbon dating. In the previous lecture we have discussed about radioactive decay and we have obtained an exponential decay curve. Here also we are following the same method to understand the age of materials. So the physical information is given here. In the atmosphere and in living organisms, the ratio of radioactive carbon C614 to ordinary C612 is constant. The ratio is always a constant. When an organism dies, its absorption of C614 by breathing and eating terminates. Hence, one can estimate the age of the fossil by comparing the radioactive carbon ratio in the fossil with that in the atmosphere. To do this, one needs to know the half-life of C614, which is approximately equal to 5,715 years. So this is the physical information. So now we have a physical information. We will construct a mathematical problem associated with the physical system, and we will solve the mathematical problem and we will get the solutions and we will interpret the solution. So this is the process of modeling. So here the differential equation is equal to y dash is equal to ky. So immediately you can use variable separable method and you will get y is equal to y0 e raised to kt. Now we have some initial conditions to know the value of the constant k, and we will obtain the constant k as minus 0.0001213. Finally, we will use the information given in the problem, and we can see that the age is equal to age of this particular fossil in the given problem is equal to 5,300 years. You read the steps carefully, you can very well understand how to model radiocarbon dating using differential equation, that too by using variable separable method. Okay. Other methods show that the radiocarbon dating values are usually too small according to the recent research. This is due to variation in the carbon ratio because of industrial pollution and other factors such as nuclear testing. So that is a given information, but this is a general method to understand the age of fossils. And we have also used the differential equation here. Next, we are considering modeling of Newton's law of cooling. You can see the video. Here, a problem is given, and you can very well understand how to model this problem by the concept of Newton's law of cooling and also by using differential equations. Please listen to the video carefully.
And we want to create a differential equation based on this. So that 200 degrees is going to be the temperature of its surroundings. So for part A, let's use a capital T. So the change in temperature with respect to time, that's our rate the temperature is changing, is equal to, now it's proportional, so we need a constant of proportionality, the difference between its temperature, which we're calling T, and the temperature of its surroundings. So right there is our differential equation for this problem. And it's just based on Newton's law. So now what we're going to do is we're going to use this information that the roast is initially 20 degrees and it's at 120 degrees after 30 minutes to solve the differential equation from part A. So part B, we're going to solve our differential equation and we'll use a separation of variables. So dt over t minus 200 equals k d little t. And now let's go ahead and solve this for t. So on this side we've got ln of the absolute value of t minus 200 equals, we're doing the antiderivative of both sides, I should have mentioned that, kt plus our initial constant, we'll call it c1. Now to get these out, we know we need to make them exponents of e. So we get t minus 200 equals, now I'm going to make this a multiplicative constant. I'm not going to use c because we have c in here for Celsius already. Let's use a, where a is e to the c1, e to the kt, and we can get our general solution. So t equals 200 plus ae to the kt. Okay, well that's nice, but we need our specific solution. Well, first thing we know is this roast was initially at 20 degrees. So at time 0, we're going to plug in 0 for t. The nice part about that, if t is 0, 0 times 0, k is 0, e to the 0 is 1. So 20 equals 200 plus a, which gives us that a equals a negative 180. So we're getting a little closer to getting our general solution. Let's see where we're at. 200 minus 180 e to the kt. Next we need to find k, and that's where we're going to use this bit of information that after 30 minutes we measured it and it was at 120 degrees. So we're going to put in 120 for t equals 200 minus 180 e to the k times 30, and we are going to solve this thing for k. So to solve it for k, we might start by subtracting 200 from both sides. So that's going to give us negative 80 equals negative 180 e to the 30k, and then we can divide both sides by negative 180. And over here we've got e to the 30k. Over here we'll simplify just a little bit. There's not a whole lot we can do. It's going to be 4/9. Now to get this out of the e, this is where we can take natural log of both sides. So we get ln of 4/9 equals 30k. And we divide both sides by 30. And there's the exact value of our k. If we want it as a decimal, it's right around negative 0.027. So we can now put together our unique solution. So t equals 200 minus 180 e to the, we're doing it as a decimal, negative 0.027 t. Finally, part C, we want the temperature after being in there for an hour. We've done the whole problem in minutes, so t is automatically in minutes. So when we go to computer temperature, we need to convert, and we need to put in 60 for an hour because we're going to be looking at 60 minutes. Calculating this gives us about 164.4, and this problem was done in Celsius.
Okay, so this is the way in which you can model Newton's law of cooling, and this is a very famous physics problem. We all are doing this particular problem in the lab, so it is very helpful to understand the physics behind the Newton's law of cooling and the method of using differential equation for solving the problem. And next is we can reduce some types of differential equation to variable separable form, and this is called the extended method, and we can the reduction of differential equation to separable form. We discussed this technique for a class of ordinary differential equation particularly importance, namely for equations y dash is equal to f of y by x. Here f is any differentiable function of y by x, such as sin y by x all raised to 4 and so on. Such an ODE is sometimes called homogeneous ODE, and we will discuss this homogeneous ODE in section 1.5. This form of such an ODE suggests that we can set y by x is equal to u. Okay, y by x is equal to u. That means y is equal to ux, and you differentiate, you will get y dash is equal to u dash x plus u. Substitution into y dash equal to f of y by x then gives u dash x plus u is equal to f of u or u dash x equal to f of u minus u. We can see that if f of u minus u not equal to 0, this can be separated like du by f of u minus u is equal to dx by x. And this is the way in which you can change a differential equation to separable form. Once the separable form is obtained, you can solve it by direct integration. Next, we are considering some problems in variable separable differential equations. Okay, please listen the problems. Here we have many types of differential equation: variable separable differential equation, homogeneous differential equation, exact differential equation, linear differential equation, etc. And we will discuss all these types of differential equations in this chapter. So we have discussed about variable separable differential equation, and what we are doing is we will be doing some problems in variable separable differential equations. So first problem is dy by dx is equal to e raised to x into e raised to y. So the problem is very clear. Dy by dx is equal to e raised to x into e raised to y. And variable separable form, you know that one side you will be having a function of one variable, and in another side you will be a function of another variable. So it is very easy to change the given differential equation to separable variable form. And you can see that this differential equation is basically a function of y and x. So here you can manipulate like this. Ey can be changed to the LHS, and x can be changed. X can be brought together to the right hand side. So you will be getting dy by e raised to y is equal to e raised to x dx. So this is very clear. This is separable form. Dy by ey is equal to e raised to x dx. So the next method is direct integration. Very simple. Integral dy by e raised to y is equal to integral e raised to x dx. So by using the basic rules of integration, you will get e raised to minus y divided by minus 1 is equal to e raised to x plus c. C is the constant here. Now you can manipulate e raised to minus y plus e raised to x plus c equal to 0. So this is the solution. Very simple solution. So the differential equation is solved by using what? By using separable method, variable separable method. So this is very clear. I think it is very simple to understand this problem. Dy by dx is equal to e raised to x into e raised to y. That can be solved by using variable separable method or separation of variables. So this is the first problem. Next, we can consider another problem. So the steps: separating the variables, integrating, and insert the constant. So this is the step. Okay. So second problem is dy by dx plus y square equal to 0. So basically this is a differential equation of first order differential equation. Dy by dx plus y square is equal to 0. So the steps are separate variable separable form, integration, insert the constant, and write the solution beautifully by rearranging. So LHS y function, in the RHS you will be getting a function of x only. So you can do the manipulation to get dy by dx is equal to minus y square, or you can write dy by minus y square is equal to dx. So once that is obtained, dy by minus y square equal to dx, then you can say that that is variable separable form. Then you can immediately integrate. Integral dy by minus y square is equal to integral dx. And you know that integral yn is equal to y raised to n plus 1 divided by n plus 1. And here instead of n you will be having minus 2. You can do the manipulations. Y raised to minus 2 plus 1 divided by minus of minus 2 plus 1 is equal to x plus c. Y raised to minus 1 is equal to x plus c, and y is equal to 1 by x plus c. So this is the solution. Y is equal to 1 by x plus c. Next problem, dy by dx is equal to 1 plus x plus y plus xy. This problem is a bit different. dy by dx is equal to 1 plus x plus y plus xy. So here you can see that the algebraic manipulations to change the given differential equation to variable separable method. Dy by dx is equal to 1 plus x plus y is taken outside, y of 1 plus x, and you can see that 1 plus x plus y of 1 plus x can be written as 1 plus x into 1 plus y. So that is very important. So you observe the given differential equation, and you must have the form of variable separable in your mind, and you do appropriate algebraic manipulations to change the given differential equation to variable separable form. So how can you do this kind of manipulation? The only technique is practicing. So you have to do many problems, then only you will be getting this kind of idea. Otherwise you will never get. So practicing is the best method to do solutions or to solve the problems. So practice makes everything perfect. So this is the method. So dy by 1 plus y is equal to dx into 1 plus x. Immediate integration gives log of 1 plus y is equal to x plus x square by 2 plus c. You know that integral of 1 by something is always is equal to logarithm of that particular thing. So log 1 plus y is equal to x plus x square by 2 plus c. So this is the way in which you can do the problem. So log 1 plus y is equal to x plus x square by 2 plus c. Okay, so the given differential equation is changed to the variable separable method by using some algebraic manipulations. Then do the integration, then solution. Okay, next is e raised to y plus 1 cos x dx plus e raised to y sin x dy is equal to 0. Here also you can see the method separating variables, e raised to y plus 1 cos x dx is equal to e raised to minus y sin x dy. You have taken the terms two sides. Now e raised to y plus 1 sin x can be taken this side, so that you will be getting cot x. E raised to y plus x, e raised to y plus 1 cot x dx is equal to e raised to minus y dy. Now cot x dx is equal to e raised to minus y divided by e raised to y plus 1 dy. Okay, so this is the way. So variable separable form is reached. Cot x is equal to e raised to minus y divided by e raised to minus y plus 1 dy. So LHS is a function of x, RHS is a function of y. So just integrate. Direct integration, log integral of cot x is equal to log sin x, which is equal to minus log e raised to y plus 1 plus log c. Log c is very important to get a simple form for the solution. Log of sin x is equal to minus log e raised to y plus 1 plus log c. Okay, so this is the way in which you can do problems. So this is example. In example 4 we have considered the differential equation e raised to y plus 1 cos x dx is equal to e raised to y sin x dy equals 0. Okay, so care should be taken to write the constant in terms of logarithm. Log sin x is equal to minus log e raised to y plus 1 plus log c. Okay, now you can manipulate log sin x plus, that can be taken on this side, log e raised to y plus 1 is equal to log z. Logarithm can be taken outside sin x into log a plus log b, that you know, log a into b. Using that fact, you can manipulate the things, and you will be getting a nice solution. Sin x of e raised to y plus 1 equal to c. Log c can be written c also, because basically it is a constant. Log c is another constant c. So sin x into e raised to y plus 1 equal to c. So this is a perfect solution for the given differential equation. So these are the things that we have discussed so far. We have discussed some problems also. You can do many more problems by seeing the exercise in your text for study, and also you can do problems from various mathematics textbook. So this is for now. References: Advanced Engineering Mathematics by Kreyszig, and 2 YouTube videos are included in my lectures, that is also given as references. Thank you very much, and we will see soon. Please ask and questions, and my address is given. Thank you very much.